All right, here we go. Number 11. This time I'm at home because we're going to get a terrible snow and ice storm today. Didn't want to be at work. So I did a Google search for physics homework 8 solution or something like that. And here's what we got. So we'll go ahead and get started here. Assuming I can hit play. There we go.
So we are looking today at problem 14.56 from the Lesson 18 Homework on Mastering Physics. So we're looking at a car with a total mass with its passengers driving on a washboard road with bumps spaced 5.4 meters apart.
So 1,800 kilograms for a car. That sounds like a lot to me, actually. That's a pretty heavy car with passengers. So this is a pretty heavy car. I'm thinking maybe more like my van than my sedan. Keep that in mind here.
We're going to see the fact that our car is going to bounce up and down with its maximum amplitude down this road, and it is going to be traveling at 7 meters per second. We want to know the spring constant of the car. Well, most of what we've been dealing with the spring constant of a car has been dealing with using frequency or period. If I look at the frequency equation with spring constants.
So as I'm thinking about this problem and listening to her set it up, it's really interesting because this is a really subtle problem. Basically, I think the key part of this problem for me is that this phrase here, the ride is roughest. So the ride is roughest at a certain speed. And I think what's going on here is resonance, right? So the car has a particular resonance that it wants to bounce up and down. It's hitting that resonance when it's hitting these bumps that are 5.4 meters apart when it's traveling at a certain speed. So let's first think about this. 5.4 meters apart. Okay, so a car is probably 2 or 3 meters. And so this is pretty closely spaced bumps. And then 7 meters per second is what, maybe 20 miles an hour, something like that. So not going that fast here. I think that you'd really wreck things if you got going with big old bumps if you're going much faster. Really interesting side point. I was driving my car once and we were towing a trailer, and the car did not have the best suspension and stabilizers. And what we found was we would hit these bumps and we would just go up and down. I could see the trailer behind me going up and down too. And I was very nervous. And by chance, I found something out. So it was going up and down, and I think I had to, avoid something or something. And so I turned really quickly. And it turned out that the bumps went, as soon as I went sideways, boom, everything sort of settled down. And once it settled down, I realized, wait a minute, what just happened there? And so it seemed like what was happening is I was turning vertical bumps, and then I would somehow getting that energy to be more lateral. And it turned out my car had much better lateral stabilizers than it had vertical stabilizers. And so for the rest of that drive, that's what I did. If it felt like it was getting out of control, I would really quickly yank the wheel and smooth things out. So I've never really done a thorough analysis of that, but I'll tell you, it worked. So I think there's something really interesting there.
It's a mass. We see the frequency. Oops, that's a bad color. All right. We see the frequency is equal to 1 over 2 pi times the square root of...
So it's interesting. I was just looking at her write this, and she was about to finish it, and I know that K and M are going to be in there. And, I'm not teaching this stuff right now, so this isn't directly in my mind. And I thought, oh, it's K over M. And then I just had this brief moment of pause, like, oh, wait a minute, it's M over K. So how would I resolve that short of looking it up? So let's see here. If the spring is stronger, I would expect the frequency to go up. So I'm pretty sure K is in the numerator. Let's talk about the mass. If the mass is heavier, I think everything kind of slows down. So I think mass is going to be in the denominator.
K over M.
Nailed it.
We can rearrange this equation to get K by itself. We do this for a lot of the problems we've done for this particular homework. When we do that, we get K is equal to 2 pi F.
So that's really interesting. So she knows that this problem is asking about the spring constant. And, so she's like, okay, well, what do we have that has the spring constant? And what's fascinating about this is that frequency is not given in this problem. And so that's actually going to be the hard work of this problem, but she's trying to set it up. She's like, look, here's the stuff we know. Here's what we're kind of used to dealing with. And then I think that my guess is she's going to say something like, okay, so how the heck do we do this? And then she's going to be able to use the, the other information to get the frequency, which is the thing that's not given.
Squared times m. So this is great and fantastic. We have m, we know 2 pi, but what do we do with f? Well, now we actually need to pull some information we just learned in lesson 19.
Exactly.
I know, not fair. But when we do that,
not
we
fair.
know that
We have to use old information.
Is equal to wavelength times frequency.
Very cool.
Well, wavelength in this particular case would be the separations between the bumps. That speed is how fast the car is moving. When we get that, we see that frequency is equal to...
So that's really subtle, right? So the bumps on the road are not moving. So that's not actually a wave. The car is moving. But I think it's totally legit to say the car's standing still and the bumps are coming your way, right? And if you do it that way, then it does look like a wave is coming your way. And then this particular setup works perfectly fine. I think that if you were to say, what if the student were to say, but that's not what's really happened. I know for sure the car is moving, and maybe they haven't studied relativity yet. You would have to do this a little bit differently. I think if you're going for frequency, you'd say, okay, well, how long is it going to take the car to go from one peak to the next? And they would be doing the exact same math as what's in here. So in this problem, thinking about the car coming towards you, a wave coming towards you, boom, the wavelength, we're going to be able to get the frequency pretty quick.
Wave speed divided by wavelength. In the context of the problem I have here, my wave speed would be 7 meters per second, and my wavelength would be 5.4.
All right, so that's a frequency of about, just over 1 hertz. So this car is going kind of like this, wonk, which reminds me exactly of what my car was doing so many years ago. And then, so that means that F is roughly 1, mass is a gigantic number. So this is going to be a huge spring constant. Normally the spring constants that students are dealing with in like lab or whatever, it's these teeny tiny little springs. You can do this to it pretty easily. You hang a mass on it and it goes like that pretty easily. But car springs are a whole different beast. And a lot of people's experience with car springs are those crazy animals that you sit on at the playground. And of course, you're not doing this with those springs. You're doing this bending action, and people think of those as being very, very slow. And so if you were to accidentally say, oh, well, that's the natural frequency of that spring when a person of my size is onto it, you'd be way off. Ask yourself a very different question. What is this frequency when you're sitting on it? So we're expecting here a monster number. I'm going to do my guess here, 36, round that up to 40 times 1800. So about 7... maybe 100,000
meters. All right, and I'd get some frequency. This number would then go into frequency here.
Love that. I love showing where it's going to go. Remind, like, hey, we've been doing all this work. It has to go somewhere. Awesome. All right. So very, very interesting. I think that a very straightforward problem that had some really interesting twists and turns in it. I think that the idea of the frame of reference is fascinating. I thought she did a great job of saying, look, here's the stuff that we know, and here's what we are looking for. All right. Well, that's it for today. A nice short one using different technology. Hopefully this worked out. And remember, physics teachers are awesome.